Autonomous intralogistic processes, in an industrial context, are the focus of Demonstrator 3. A so-called fleet manager application processes data for goods, routes and positions, and provided them to several AMRs. These AMRs emulate human senses using AI and various sensors to enable autonomous global load handling processes from A to B. Demo 3 covers all process elements in a full holistic approach. In Demo 3, elements from BB2, BB3, BB8 and BB10 are used, which underlines the interdisciplinary character and enables the autonomous shaping of Demo 3 in the IMOCO context. Demo 3 follows the IMOCO4.E framework. In all 4 layers, new approaches are pursued, which have been tested and implemented with the consortium partners. Agentization. AMR-centered fulfillment system requires scalable and flexible fleet management solutions due to constantly changing requirements in fleet size and heterogeneity, as well as system loads. Here logical AMR agents, responsible for individual AMRs, and logical domain agents responsible for fleet coordination are used. AMRs self-register with the module orchestrator of the fleet management on demand. This results in starting up a corresponding logical agent that in turn registers with the responsible domain. The AMR is now ready to receive orders for actions. Load handling. For the pose estimation, a custom deep object pose estimation (DOPE) model based on synthetic data was trained. The approach avoids manual labeling of real training data and makes the estimation robust. The deploying of the model to a Jetson board and the development of a semi-automated method to annotate real-world data using a motion capture system is started. With the pose estimation model trained on synthetic data, as shown in the first video, we can successfully estimate the pose of a pallet within the second video. To pick up loads, the real-time pose estimation is fed into a control loop. A model predictive control algorithm uses the relative pose of the load carrier and the kinematic model of the vehicle to calculate the optimal velocity. Through the feedback loop of pose estimation and model predictive control, the AMR acts optimal in the environment. Coordinated path planning. A new transport order is assigned to the logical agent, which requests the route agent for calculating a coordinated path. The route agent searches the topological graph for a conflict-free path mentioning time windows of already assigned paths. The generated path is handed over to the physical agent for path execution. Based on the allocated segments from the space coordination, the physical agent combines the segments to a corridor, which restricts the space applicable to navigation. Within this corridor, the navigation system of the vehicle plans the path and executes it autonomously. Route assistance with radar and HMI. For route assistance, a state-of-the-art radar algorithm was implemented. At this point, the radar was not being able to distinguish between moving and non-moving objects. This was overcome by implementing a new algorithm called velocity estimation. First POC results. Successful measurement of physically detectable targets in range, velocity, and angle up to 13.5 m by variation of AMR speed and direction. An easy way to evaluate user experience of encounters with AMRs would be using virtual reality. To evaluate validity of VR experiments, also for real-world encounters, a comparative test was applied. Identical encounters were experienced and rated by test persons in VR and real world. Load delivery. After reaching the road network entry point of the drop-off zone, the vehicle scans the drop-off area, defines the turn point and the drop-off point based on the given scenario, and calculates the appropriate path. By using autonomous navigation features, the vehicle approaches the drop-off point by bypassing obstacles.